Okay, so this is the smallest a such that Frobenius to the power of a is equal to identity on K. Right? The identity element of the Galois group is the identity map. Sorry, on FQ. As you can tell, I recorded all these videos on the same day, so it's been a long day. So I keep making more and more mistakes, so just be patient with me, please. So the order of Frobenius, okay, so it's the smallest a such that Frobenius to the power of a is identity. Okay, so now let's see. So what does it mean for Frobenius to the power of a to be identity? Well, it means that, okay, so this means, so what does this mean? This means that for every alpha in FQ, Frobenius to the power of a applied to alpha, which is alpha to the power of p to the power of a, alpha to the power of p to the power of a. So this is the image of alpha under Frobenius to the power of a. This should be equal to, well, identity applied to alpha. So alpha. So we're looking for the smallest a greater than or equal to 1 such that alpha to the power of p to the power of a is equal to alpha for every alpha in FQ. Okay, let me get the camera, sorry. Okay, so now what does this mean? So, well, this is to say that you want alpha to be a root So we're looking for the smallest a such that every alpha in FQ is a root of x to the power of p to the power of a minus x. Well, this is a polynomial of degree p to the power of a. It can have at most p to the power of a roots. Well, you want every element of FQ to be a root of it, so you want it to have at least q roots, right? So that means that p to the power of a, so this can have at most, p to the power of a roots. And we want every element of FQ to be a root of it. So we want it to have at least q roots, which is to say, so what do we get? We must have p to the power of a is bigger than or equal to q, which is p to the power of n. So a is greater than or equal to n. But on the other hand, if I do take a to be n, so now I'm looking at x to the power of p to the power of n minus x, this guy, well, indeed does have every element of FQ as a root. Remember, q was with p to the power of n. This does indeed vanish at every alpha in FQ. So the order of Frobenius is exactly equal to n. Frobenius to the power of n is equal to identity. And Frobenius to any power less than n can't be equal to identity. If Frobenius to any power is equal to identity, that power is at least n. So the order of the Frobenius is exactly equal to n. Or if you wish, once you're here, what you've argued is that Frobenius to any power smaller than n is not identity. Also, the order of Frobenius is not less than n, but now, well, from group theory, the order is at most n, so the order actually has to be equal to n. Okay? So now the order of Frobenius is equal to n, and now, okay, so what do we get? We've got this group, the Galois group. This group is a group of order n. This is a group of order n. We found an element of order n. Namely Frobenius. Contains an element of order n. Namely Frobenius. So if I have a group of order n, and if it has an element of order n, what does it mean? It means that it's cyclic generated by that element. Right? The subgroup generated by Frobenius, it has n elements, because Frobenius has order n. The subgroup generated by Frobenius has n elements. Well, my whole group has n elements, so that subgroup has to be the entire group. So it follows that the Galois group of Fq over Fp is cyclic generated by Frobenius. So let's record this as a theorem. The Galois group of Fq over Fp is cyclic of order. Okay, so if Q is p to the power of n, the Galois group of Fq over Fp is cyclic of order n, generated by Frobenius. Frobenius, remember, it's the map that sends any element alpha to the power of p. So the Galois group of finite, the Galois group of a finite extension of Fp is always cyclic and generated by the Frobenius elements. So that's a very, very important result. We should remember this. Thank you.